Okay, and we can wrap up this first study session in fixed income with this material on valuing bonds with embedded options. I've talked to a number of candidates who actually felt like this was the most difficult reading in the Level 2 curriculum. Not something that I particularly think is right. It's certainly not the hardest for me anyway, but it is something that may be a little different than what you're used to seeing elsewhere. So if this is something that's hard for you, it is something that you can get on top of. So it's something that just may take a little more effort, working a few more problems, those types of things. But what we're basically going to do here is two really important things. One, we're going to talk about how you would value a bond with an embedded option. And as part of that discussion, we are going to talk about spread measures. And I would say that both of those things are highly testable material. So actually going in and knowing how to use the binomial interest rate model, which is where we're going to start, and then translating that into the three spread measures that we're going to see in the Level 2 curriculum. That is the nominal spread, the Z spread, also called the zero volatility spread, or if you're in Canada or the UK, the Z spread, and then the OAS or option adjusted spread. I think the OAS is the hardest of the three to understand. We'll see that reviewed several times as we progress through the remaining fixed income material that is here and in the asset-backed stuff. So if you don't get it exactly the first time, don't worry about it. We're going to talk about it several times before we finish. So with that as an introduction, let's move into the material. So here we're going to be using the binomial interest rate model. Now remember, there are two binomial models in the curriculum that we're going to be dealing with here at Level 2. One is the binomial stock option pricing model. The one we see here is the binomial interest rate model. They are both binomial, meaning that we have a starting place and one of two things can happen in the next period. That is, we can go to an up state or a down state. And when we do the binomial stock option pricing model, we are essentially building a stock price tree. You will be responsible for building the stock price tree. Here, when we're doing the binomial interest rate model, then we're in a little bit different world. So the tree represents possible interest rate paths. Okay, one of the big differences between this and the stock option model is here we assume there's an equal probability of an up move or a down move. So the probability of moving, so we start with an existing interest rate and we can either move up to some higher interest rate or down to some lower interest rate with equal probability. So there's a 50% chance of an up move, 50% chance of a down move. That will be different when we get to the binomial stock option pricing model. So make sure you separate those two things in your mind. So equal probabilities here. But one of the big differences between what we see here and what we'll see in the stock option model is you don't have to actually build the tree, the interest rate tree here. You will have to build a stock price tree, but all you need to do is know how to use the interest rate tree on the exam. So building the interest rate tree actually requires a bootstrapping process and then a calibration process. So it's relatively advanced and clearly beyond the scope of the curriculum. It's nothing you couldn't handle. It's just that it is very time consuming and we just simply don't have room for it in the curriculum is the reason it's not here. Personally, I'm grateful for that. Actually going through the mechanics of building the tree, the bootstrapping process does get a little cumbersome after a while. So this is a binomial interest rate tree. We have interest rates today. This is this is the time zero spot rate. So if we have rates that are here, if we have cash flows that are here at time 1, we want to discount them back to time 0, we're going to use the rate at the 0 node. Likewise, if we have cash flows down here, we're going to discount them back. So if we look at the interest rate up here, the up node at time 1, then if we have cash flows that are here, we're going to discount them back at this interest rate, the up node at time 1, or down here we can discount them back. In fact, all we're doing with any of the binomial models is finding an expected value and discounting back through the tree. So the trick here is going to be to find the expected value, discount them back. There's a 50% probability of each of them, so we multiply by their probabilities. That will give us a value here. We'll do the same thing at the lower node down here and then finally bring it home. So all of the binomial models are essentially a backwards induction. You're going to know something at the end of the process and you're going to want to bring it back to the beginning through the tree. Here it's going to be bond values. When we do binomial with the binomial stock option pricing model, it's going to be option payoffs for European options. We'll also see, option payoffs on bonds when we get to the derivatives material. So one of the complexities of the tree is that it should be arbitrage free. And what that means is you create the tree. So we're going to create a tree. We're going to make some assumptions about volatility. We're going to look at what current interest rates are. And then we're going to calibrate the tree to be arbitrage free, which means the tree should give us the value for looking at a treasury security. It should give us the value of the on-the-run treasury security. Now, the thing to remember is that while the tree has to be arbitrage free, which for us is really just a theoretical concept, we're not going to be calibrating, but while the tree has to be arbitrage free, there are an infinite number of arbitrage free trees. So there's one tree with a volatility of 8% and one with a volatility of 8.01%. So we make volatility assumptions that determine the width of the branches, and depending on our assumption about volatility, we then calibrate the tree by taking the on-the-run treasury security and forcing the tree to reflect a certain set of values. What we actually do is we come up with the very lowest, we take the very lowest set of branches on the tree. Those are deterministic, and then the space between the lowest point for any given period and the interest rate above it is determined by a specific formula, but that is not part of the curriculum. So remind yourself that this should be arbitrage free, which means that if we actually use the tree to value a treasury security, it will give us the market price. So take your treasury security, run it through the valuation process. You will get the market price of the security. That's an arbitrage-free tree, but we're not actually going to be doing the arbitrage-free calibrations, and there are an infinite number of arbitrage-free trees. Okay, spread measures. So this is our first exposure to this. We're going to see it several times as we go through. But remember, there are three spread measures for which you are responsible. The first is the nominal spread, and this is probably the one you're used to. It's the one we discussed at level 1. Basically, it said we're going to take the yield on the subject bond, maybe that is a single A corporate bond, and we're going to subtract off the treasury security. So it's the difference between the bond yield and the yield on a comparable maturity government treasury security is the way we would normally calculate that, although we could do, as a version of the nominal spread, the yield on a single A security minus a triple A security. That would also be a credit spread measure. Normally, the nominal spread is going to be as opposed to a similar maturity treasury. Okay, the thing to remember about the nominal spread on the exam is that we don't want to use it. All right? So there's not ever going to be a situation on the exam where we can use the nominal spread. There are situations where the nominal spread and the z-spread will be very similar, perhaps almost equal, but we're still not going to be using the nominal spread. So that leaves us with the two important measures, okay, which for our purposes are going to be the z-spread and the OAS. All right, so what is the z-spread? Well, the z-spread is the spread that you add to each rate on the spot rate curve that makes the present value of the cash flows equal to the market price. Now, let's think about what that means for a moment. Okay, so if we draw us a spot rate curve, so we're looking at time, and we're looking at that against spot rates. So I'm going to put an S there. And we have this set of spot rate curves. And this is called the theoretical spot rate curve for treasuries, right? Okay, so we have the theoretical spot rate curve for treasuries. Well, if we go and we say, well, look, we want to look at our, AA bond. So we go through and we find out each of the cash flows. So we take each cash flow from our coupon AA bond, we discount them at these spot rates, and we come back and we get a model price equal to, let's say, $971. All right? So that's what we get for the price of the bond from our model. Well, that's great, but then when we go and look in the newspaper and we look at the market price, what we get for the value of the bond is $900 and let's call it $60 here. All right. Well, what happened? We ended up with a price from our model that was too high. Well, is that surprising? Well, remember, this is called the theoretical spot rate curve for treasuries. So these interest rates were determined based on treasury securities, that is risk-free securities, whereas what we're dealing with here are risky securities. That is a AA bond. So if we use risk-free rates to discount the cash flows from our AA bond, the interest rates or the discount rates are too low. Obviously, we're going to get a price that is too high. So what we can do now is we can go back and say, well, let's go back and let's add a spread to each of the spot rates on this theoretical spot rate curve. So we go and we do that. We add the same, let's call it, 50 basis points, and we come up with a price of $965. Well, in that case, have we forced the model price to be equal to the market price? Well, we haven't. So what if we go back now and we add an even bigger spread, okay, so which I'll represent with this dark blue line. So we add now 60 basis points to every spot rate on the theoretical spot rate curve for treasuries, and we get a value of $960. What have we done? We've forced the model price to be equal to the market price. When we find the spread that does that, okay, with a theoretical spot rate curve, think of that as something that exists in nature. So we got that from treasuries. When we find the spread that we can add to that, that will force the model price to be equal to the market price. In this case, we said it was 60 basis points. Well, that is the Z spread. So the spread that you add to every interest rate on the theoretical spot rate curve for treasuries such that the market price is equal to the model price. This model is what we get from all this discounting. That is the Z spread, or the zero volatility spread, or the Z spread, or whatever we want to call it. All right? So this is one of the examples of why you had to understand where this theoretical spot rate curve for treasuries comes from, because you have to understand that in order to understand the Z spread. So we kept trying different spreads until we forced the model price, that is from us discounting the cash flows at these spot prices or spot rates plus a spread, and then we did that until we forced the model price to be equal to the market price. Then we have found the Z spread. All right? So that's our Z spread in the sense that we've now gone through and done this iterative exercise. This is going to be an important measure. What we're ultimately going to say is that this is going to be fine if there's no optionality. That leaves us with needing to talk about the OAS. And the OAS is going to be more difficult to calculate and maybe a little more difficult to understand. But basically, this is going to be the spread added to each rate in the binomial interest rate tree that makes the bond value calculated from the model equal to the market price. So both of these, the Z spread and the OAS, is an iterative process where we're going to take some model, either the theoretical spot rate curve or the binomial interest rate curve, and we're going to add spreads until we force the model price to be equal to the market price. Let's talk a little bit more about these spread measures. Okay, so what we'll see is that for a short-term security with a relatively flat yield curve, the nominal spread and the Z spread will be almost the same. But the difference gets larger if the more sloped the curve is, the longer the maturity of the securities, and if the security we're talking about repays principal over time, something like a mortgage-backed security. So if we were talking about a really flat yield curve for a 2-year security, well, the nominal spread and the Z spread would be almost the same. But if that yield curve starts sloping, if we're talking about a 20-year security, or if we're talking about a security that is amortizing, pays both interest and principal, then the Z spread and the nominal spread are going to begin to diverge. My advice, again, is to forget that you ought to know what the nominal spread is, but you can't rely on it on the exam. We're going to have to do the Z spread unless they specifically say this is a very short-term security and it has a very flat yield curve, all that sort of stuff. Well, that would make sense, but that would also be, I think, relatively remote. The OAS, the option adjusted spread, I think would be better called the option removed spread. So when we calculate a Z spread, that compensates us for 3 things. Okay? It compensates us for credit risk, it compensates us for liquidity risk, and it compensates us for option risk. So all 3 of those things have to be included in the Z spread. The OAS, the option adjusted spread, or the option removed spread, takes out the cost of the embedded option and leaves us with the compensation just for credit and liquidity risk. So this is a formula, and I'm going to get rid of some of this other chicken scratch. So this is a formula, not so much a formula as an identity that you need to know. The OAS is equal to the Z spread minus the cost of the embedded option. So what if we're talking about a bond that doesn't have any embedded options? Well, then there's no option cost, and the OAS and the Z spread are the same. Okay, so, but if there are embedded options, then there's going to be some compensation for bearing that option risk, okay, and the OAS will be smaller than the Z-spread. So the way you can think of this is we can start with the theoretical spot rate curve or spot rate benchmark, okay, and then we can look at corporate bond yields. So we can see the spread between the corporate bond yield and the spot rate curve. Well, that's the Z-spread that we just calculated. Of course, I was doing it, in little increments. I drew dots rather than a continuous curve, but nonetheless, it's the same thing. So that's the Z-spread. But remember, that has to compensate us for three things. That has to compensate us for liquidity, for credit risk, and if there's any optionality in the underlying cash flows, for option risk. What we're doing with the option adjusted spread, and we'll actually do it in a minute, is we are taking out, or we are building into the price of the bond or to the cash flows that we evaluate the impact of the option. So we're going to take out the option risk, and we're going to be left with just the amount of spread that we're getting because of the other factors, liquidity and credit risk. We'd really like to be able to adjust for liquidity risk also, so we could just compare credit risk spread to credit risk spread, or to take out all of those. So what we'd really like to have is a credit risk adjusted, liquidity adjusted, option adjusted spread. And then if the spread was greater than zero, we'd know the bond was underpriced. So it'd be a very direct measure, okay? But unfortunately, that's not going to be something that we can get. Anyway, remember, the Z spread is going to be equal to the amount of the option cost plus whatever's left over is going to be the OAS, all right? So I want to skip this next slide for just a moment. I'm going to come back to it, but I think it makes more sense to talk about the one after that first. So the question then is, when we calculate the Z-spread or when we calculate the OAS, what are we comparing it to? The discussion that we've had so far involved comparing it to U.S. Treasuries. So we know that the return on these bonds, these risky bonds, has to be greater than the Treasury, right? So we could also, however, use a sector spread. That is, we could compare a single A bond to the AAA bonds. So that would any bond sector with a higher credit rating, so the single A compared to a AAA. But we could also use a issuer specific. So if we went and looked at, say, IBM bonds, well, IBM has lots of different bonds outstanding. So we could take IBM bonds and compare them to IBM bonds. Well, then we shouldn't have any credit risk differences, and we're going to get a very direct comparison. Well, so let's see what we're actually ending up with. I'm going back a slide now. Don't like to do that too much, but every once in a while I find it unavoidable. So here, what we're talking about is the OAS that we've calculated, and if it's greater than zero. So the OAS is greater than zero. Well, if we're saying that the option adjusted spread for this bond is greater than zero, what that says is the spread on this bond is greater than and we're using an issuer benchmark, that the spread on this bond is greater than the spread for the same issuer on other bonds. So the higher the rate, the higher the spread, the higher the rate, and the lower the value of the bond. So if we compare to an issuer benchmark and we can find a positive OAS, that's a bond that's offering too much return and therefore is undervalued. The rates are high, so it's undervalued. What about the Treasury versus the sector? Well, here we're going to have to talk about what the actual OAS is versus the required OAS. We know that whatever this bond is, as long as it's not another Treasury, if they're comparing it to the Treasury, it has to have a positive OAS, right? So that's the market equilibrium. You have to have more compensation for the credit risk. So if the actual OAS is greater than the required OAS, then the bond's going to be undervalued. Same for the sector analysis. What about if the OAS is equal to zero? Well, what that says is that this bond is giving us no additional compensation for liquidity risk or credit risk over the Treasury. So it has to be overvalued. You've got to have some sort of positive OAS when you're comparing to the Treasury security if you're looking at risky bonds. Same thing for the sector. So this saying this single A bond offers no more yield after we adjust for optionality than a higher rated bond. So that means that this bond is overvalued. And of course, if we're just looking at the issuer, then it should have an OAS of 0, right? So I expect to get no additional return over the same issuer when I buy another bond from the same issuer, so the OAS should be equal to 0, so that would be fairly priced. So when you're going over this, and I realize that the first time you see this is a little complicated, concentrate on the first two rows here, and then go back and check your understanding by looking at the bottom one. Anyway, so the relative benchmark is going to be important. Are you comparing it to treasuries? Are you comparing it to higher rated bond sectors? Or are you comparing to other bonds issued by the same company, that is the specific issuer? All right, with that as a background, let's jump into the idea of valuing a bond. We'll start out with a bond that doesn't have any optionality. What we want to get to is valuing a bond with embedded options, right? But we're going to value a bond that doesn't have any embedded options, and we're going to use the binomial option pricing model to do it, okay? Or the binomial interest rate model to do it, excuse me. So anyway, the approach here, we're going to value the bond by moving backwards from the last period to the 0 period. So this is called backwards induction. How can we do that? Well, remember, we know what the bond's going to be worth in the future. We know that it's going to be worth its maturity value plus its final coupon payment. So if we know that, all we've got to do is discount back through to today using the principles embedded in the interest rate tree that we created via the binomial interest rate model. That is that it's got a 50% probability of up and a 50% probability of down. So remember, the value at maturity is known. The value in any node, okay, is the average present value of the two possible values for the next period. So if we are, looking at the node here, well, we know that the value can go up, or that we know the interest rates can go up or the interest rates can go down. We're going to find the value here, and then we're going to take the average of those and we're going to divide the whole thing by 2. Now that's supposed to be a 2. It's more like a z. Anyway, we'll divide it by 2, and then we're going to discount back in order to find the value. We're going to do this several times so you'll get to see what's going on. The discount rate is the forward rate for that node. So we use the interest rate here when we're evaluating these values that are downstream in this process. All right? So backwards induction, we start at the end and we work backwards towards the beginning. So here is our example. We're going to work with a 7% 2-year bond, no embedded options to start with. Once we do this, then we'll go back and add an embedded option. What you're going to see is it's only going to take one little change to move to valuing a bond with an embedded option. Okay, and we're going to be given the interest rate tree in order to do it. So we know that 2 years from now, so here's the maturity of the bond. Well, the value of the bond 2 years from now is going to be its maturity value plus its final coupon payment, so 107, and it doesn't matter what interest rates are. That's why this backwards induction works for bonds, because we know the value of the future. We can't use this with stocks because we don't know the value of the stock 3 years from now or whatever, right? So anyway, so there's the value of the bonds 2 years from now. What else do we know? Well, we're going to take those values and we're going to find their average, and we're going to discount them back to these nodes. So if you end up here in the up node at time 1, so we're ultimately going to draw on a node here, and we're going to say you go up and down like that. So if we end up here in the up node at time 1, well, what are we thinking from here? Well, we've got a 50% chance of getting $107 up here, and we got a 50% chance of getting $107 down here. It's not particularly interesting at the mode right before the maturity, but nonetheless, what does that tell us is the present value of the expected cash flow? Well, if we have a 50% chance of 107 plus a 50% chance of 107, that gives us an expected value here of 107, and we're just going to discount that back at 7% to find what the value of the bond would be. Excuse me, we discount that back at 8%. That's the coupon payment I see there. Anyway, so we're going to discount it back at the interest rate in that tree, the 8%. So we're going to take 107, discount it back to find the value up here. Then we're going to do the same thing to find the value here. Then we're going to say, well, what do we know what the interest rates are here? Well, when we do, we're going to take the value here and discount them back. So let me get rid of some of this chicken scratch, okay, and we'll see what's going to happen. From here, we need to know the value in the up node at time 1 and the value in the down node at time 1. We don't forget the coupon payments because that's part of the value there. We've got a 50% chance of whatever the up node value is, a 50% chance of whatever the down node value is. We're going to take those, we're going to add them together, we're going to divide by 2, and we're going to discount that back to the 0 node at 3%. Okay? So for the up node at time 1, quick review. The up node at time 1, so that's here, right? So this is time 1, this is the up node and the up node and the down node. So the up node is up here, and the down node is down here, right? Right, so here the value is equal to the average present value of the cash flows from time 2 up node. So this is the up node. We had to go up and then up again, and the up down node. So if you start here at the beginning, you go up and then you go down, that's the up down node. So we've got to find the present value of the up and the up down discounted back at this 8% that we see here. All right. So when we look at the valuation, so in the up node at time 1, okay, the up node at time 1, we had a 50% chance of getting 107, a 50% chance of getting 107. We're going to multiply by a half, right? That's because they're each equally probable by assumption and always so under the binomial interest rate model. We're going to discount those back at 8% and we're going to get 9907, right? Okay, then what about the down node or the lower node at time 1? Well, we've got a 50% chance of getting 107, a 50% chance of getting 107. They're equally probable, but here we're discounting at 5%, so we get 101.90 as the value in the down node at time 1. So if we come back over here, what we would see is that up here we've got 9907. And that's the pretty poor 9 there. And here we had 101.90, right? We still have this $7 that goes in there. So up here we're going to get 9907 plus $7. Down here we're going to get 101.90 plus $7. Well, we're going to find the actuarially fair value of that. And this, so that is add them together, divide by 2, and then discount them back at 3%. To get back here to the 0 node at time 1. So looking again, going back this slide to the slide that we'd already been to, well, what is the value at the 0 node? Well, here is the value in the up node at time 1, 9907. So we got that from up here. And here is the 101.90. We got that from right here. We're discounting back at 3%. They're equally probable, and that is going to give us the value of the bond today at the 0 node of 104.35. So anyway, so that is the backwards induction process. You see that we had to go to the up node and we had to go downstream further, bring those cash flows back, the down node, bring them back, and we could do this for 40 periods too. Now I doubt you would see more than 3 periods on the exam just because it takes a little bit of time, but nonetheless this is something you should be ready to do. So if we wanted to look at this in all its glory now, there's what we knew when we started. At the end of 2 years, the bonds were going to be worth 107. If we discounted those back to today, we calculated a value of 9907 up here and 101.90 here. Well, now what we're going to do is we're going to take those back to today, not forgetting about the coupon payments. So if you're Andy Holmes, you get in a rush on the exam, you get that 101.90 and that 9907, you immediately want to average those together and multiply by a half and discount back 3%, and you end up being off almost $7, right? So anyway, you have to not forget about the coupon payments, but we've used this backwards induction process in order to value this bond that does not have any embedded options. Now remember, the title of this reading was Valuing Bonds with Embedded Options. So what we need to do now is take this same methodology and value a bond that has an embedded option. That is a callable bond or a puttable bond or a capped floater or anything else that might have bonds with some sort of optionality. So the thing to remember here is if you can do this for a non-callable bond, then you can probably do this for a callable bond because there's only one little change that we have to make, all right? So before we get started, a couple of caveats here. if we're gonna go to a callable bond or any bond with an embedded option, we're gonna need a rule for how that option would be exercised. So in other words, the firm's gonna exercise their option when interest rates fall. But if the coupon rate on this is 7% and interest rates fall to 6.99%, well, transactions costs would probably prevent them from exercising their option, right? So we'd need some sort of rule here, and as a default rule on the exam, if they don't say anything else, if the option's in the money, forget about transactions cost, they'll exercise the option. We also need to know the exercise price, here a call price since we're dealing with a callable bond, but this is what we're going to see is going to be the limit for each node's value. So if the price that we calculate would go above the call price, then they're going to exercise their option. So we have to have a call rule and a call price. Let's take our same example, that is a 7% 2-year bond, and extend it now to a callable example where the bond is callable at 100 at the end of the first year. Okay, so it's callable at 100. Our call rule is going to be if the price goes above 100, they're going to exercise their call, all right? So calculate the bond value today. How do we do that? Well, if we come up here and we say, all right, we know that the value of the bonds at maturity, if they haven't been exercised, is going to be 100. So we already know that. So we can go in and we can say, well, let's do exactly what we did before and calculate the value at time 1. So if you're standing here in the up node at time 1, well, we already told the story. You got a 50% chance of this and a 50% chance of this. You're discounting it back at 8%, and we ended up with a value of 99.07. We already calculated that. Then we also went down here and said, well, you got a 50% chance. Let me get rid of some of this chicken scratch. You got a 50% chance of 107, a 50% chance of 107. We're going to discount that back at 5%, and we get 101.90. Okay, well, here's the question you have to ask yourself. If we calculate a value of 99.07, will the firm exercise their option to buy this bond back at 100? Well, no, they won't. They have the right to buy it at 100 if they want to. If they want to retire the bonds, they're not going to pay 100. They'll go in the market and buy them at 99.07. But the situation is different down here in the down node at time 1. Now the value has gone above the exercise price. So what we're going to do is we're going to assume the firm exercises. So if you're holding this bond here, you're not going to get 101.90. What you're going to get, okay, is 100. So the process for evaluating or valuing bonds with embedded options is at each node you ask yourself, will the option be exercised? Up here, it would not be exercised, so we didn't do anything differently. Down here, it will be exercised, so we don't use the calculated value, we use the exercise price. And other than that, everything else is the same, because now as we go back to the 0 node, well, we've got a 50% chance of getting 99.07 plus the coupon, and a 50% chance of getting 100 exercise price plus the final coupon payment, and we discount that, we discount that back at 3%, and we get 103.43. So last time we did this, we calculated a value of 104.35. The value is lower for the callable bond. Does that make sense? Well, all else equal, the firm having the right to call the bond away from you is a bad thing for the bondholder. The bondholder won't pay as much. We would expect the value of the callable bond to be lower. So we ended up here with a value for the callable bond of 103.43 from our model. You should, if you got this down, you worked the example with us, or with me, then call your mom, tell her that you have valued your first bond with an embedded option. She'll be very proud. She may also ask, what's a bond with an embedded option? But anyway, she'll be proud of you nonetheless, all right? So 103.43 is the value of the bond given this embedded option that impacted this lower node at time 1. Now, this is bonds with, the title of this reading isn't valuing callable bonds, it's valuing bonds with embedded options. Well, there are many types of embedded options, but the other common one would be a puttable bond. Okay, the point here is that they're all valued the same way. when you're going through this binomial process, at every node, you simply ask yourself, will the holder of the option exercise? And if they will exercise, and here, of course, we're talking about interest rate sensitive embedded options. We're going to change that in a little while. But if you're looking at these embedded options, okay, we're going to say, will the option be exercised? And if it will be, then you use the exercise price. And if it's not, then you just don't do anything. You'd use the calculated price, just like when we were valuing the bonds that did not have embedded options. All right? Now, what have we done? We've looked at this bond, 7%, 2 years. We had the same binomial interest rate tree. The only difference between those two values that we calculated was that one of them was callable and one of them wasn't. Well, if we have that information, we know the value of the non-callable bond was 104.35, the value of the callable bond was 103.43, and the only difference between those two was the existence of the call option. Then, by subtracting one from the other, we can come up with the value of the embedded call. So the value of the non-callable minus the value of the callable equals the value of the embedded call. This is something I would make sure that I understood and put on my formula sheet if I had any problems with that. We could do the same thing with a puttable bond. Okay, and here we would have the value of the puttable bond, which of course is more valuable because that's an option that resides with the bond holder, not with the firm. So you would pay more for that, minus the value of the non-puttable bond. That would give us the value of the embedded put. So once again, I would make sure that I knew how to do that on the exam. All right, now a subtle but very important point, okay, and that is volatility and embedded options. Okay, and in order to understand this, you have to make sure that you internalize this first bullet point here, all right? So straight bond values are not impacted by volatility. So let's think, and you may not have covered the derivatives material yet, but what you're going to see when you look at something like the Black-Scholes option pricing model, okay, is we're valuing an option. Well, an option is going to be a function of 5 values in a simple world. Okay, the spot price, the exercise price, time to maturity, interest rates, and volatility. All right, so those are going to be the 5 factors that impact the value of an option. Well, what we say, and we'll talk about this when we do the derivatives material, but options are a volatility play, meaning the higher the volatility, the greater the value of the option. So what do we have here? If we're taking a non-callable bond and a callable bond, the difference is the value of the call. What happens if rate volatility increases? Now make sure to distinguish between a change in interest rates and a change in interest rate volatility. So if we're looking, over time, there's a T and here is, an R, okay, and you see interest rates, jump up, well, of course, interest rates increasing are going to impact the value of straight bonds, okay, but what we're talking about here is interest rate volatility. So if interest rates are going up and down like this, okay, that would imply one level of volatility, and then something happens and now interest rates are on average the same, but the volatility is greater. Well, then rate volatility has increased. Volatility impacts the value of options, but it does not impact the value of straight bonds. So volatility, not a change in the level of interest rates, but in the volatility of interest rates. What does that mean? We know that the value of the option is increasing. We know that the value of the non-callable bond is not impacted. So if rate volatility increases, the value of a callable bond will fall. So if we have rate volatility increases, the value of the call option has to go up. So we know that the value of the non-callable bond is unchanged by rate volatility. So that means the value of the callable bond must be falling. I would say this is an important concept for exam purposes. All right. Now, let's go back and look at this option adjusted spread thing again, okay? So we've already gone through and we valued this bond with the embedded option, and we came up with a price of 103.43 if I'm not mistaken, right? So we used our model, right? Model. That's a terrible E. And we got 103, was it 43? I think that's right. Well, what happens if we go to the newspaper and we see that the market price for this bond is equal to, let's say, just as an example, 102, let's call it 71, all right? 102.71. Well, now our model price and our market price are not the same. Well, what we can do is we can go back and we can add 20 basis points to every interest rate in the interest rate tree, the binomial interest rate tree. If we do that, we're adding spread to it, we're increasing every interest rate, that's going to drive down the value of the bond, right? So if we added 20 basis points, we'd see this would fall to, 103, we'll call it, I don't know, 03 or something like that. Well, what would happen if we added 50 basis points to every interest rate in the interest rate tree? Well, then if we could force the model, if that would force the model price to be equal to the market price, then we would have discovered, okay, the option adjusted spread. So if we go to the next slide, and so here we go through and we do exactly what we did previously. So we're looking at the same values that we looked at previously, and we say, look, here's the value in the up node at time 1, the lower node at time 1. We account for the optionality here, so we're using the exercise price in the lower node rather than the calculated value. But instead of discounting to the upper node at 8%, we're discounting at 8.5%. Instead of discounting to the lower node at 5%, we're discounting at 5.5%. Instead of discounting to the zero node at 3%, well, we're discounting at 3.5%, so we're adding 50 basis points to every interest rate in the binomial interest rate tree. And when we do that, now we come up with a value of 102.71, which was the same as the market price, almost like I've seen these slides before, isn't it? Okay, then we have calculated the option adjusted spread. Okay, so the OAS is the interest rate spread that we add to every interest rate in the binomial interest rate tree so that we force the model price to be equal to the market price. The model price to be equal to the market price. When we do that, we have calculated the option adjusted spread, what I would call the option removed spread. So to look at it in all its glory here, well, once again, we know that the value of the bonds at maturity, okay, we're going to discount these back not at the rates that we calculated in the tree, but at the rates plus a constant spread. And if we do that, we get 102.71, which we said was the newspaper or the market price. Therefore, we end up with this situation where the model price is equal to the market price. This tells me that the option adjusted spread is 50 basis points. All right. So that means after I take out the impact of the options, so I've already included what the option is going to do to me. Instead of getting in the lower node at time 1, instead of getting 101.42, I'm only going to get 100. So I have impounded the cash flow impacts of the options into my calculation. So I've impounded that. I have adjusted for it. I have taken that part of the return out, if you want to think of it that way. Then I have found the option adjusted spread. All right. So one more look at these benchmark things, and then we can talk about some duration measures and then convertible bonds, and we'll be done with this reading. So here, if the benchmark is a higher rated bond sector, so we're looking at a single A bond and we are going to compare that to a higher rated sector. Okay, that could be the treasury bonds, it could be even, AAA or AA bonds, something like that, any sector that's higher rated. Well, when we calculate the nominal and the Z spread, that has to compensate us for any credit risk. Okay, it has to compensate us for any liquidity risk, and if there's any embedded optionality, it has to compensate us for the option risk. Notice that when we do the OAS, there's nothing here, right? We are looking at the compensation, the spread that we earn for bearing the liquidity risk and the credit risk. We have already impounded the impact of the option into this OAS. Now, we'll review this again when we get to the next study session, but the rule is going to be this: never use the nominal spread. The Z spread can be used for any instrument that doesn't have embedded options. the OAS has to be used if you are dealing with securities that have embedded options. We're actually, before we're done, we're going to have two different OAS. This is one of them, the OAS via the binomial model. Okay, but if there's any embedded options, then you have to have the OAS. All right, so that's the bottom line. Never use the nominal. Use the Z-spread if you're talking about a straight bond. Use the OAS for any bond or any fixed income security that has embedded options. All right. Okay, so here is, if we're looking at it relative to the specific issuer. So you're looking at the nominal and Z-spread. That's a compensation for option risk and liquidity risk. Because we're using the same issuer, there's no difference in credit risk, so we don't have to worry about that. The OAS, once again, takes out the option risk, so it is the option removed spread. Okay. All right, what about effective duration and convexity? These are the formulas that you saw at level 1. I would put these on my formula sheet, so I'm putting an FS here. Remember, you don't bring a formula sheet in the exam, but you ought to be writing your formulas down somewhere so that you have them in a convenient place to study them. And then it'll facilitate memorization. So effective duration, this is the value of the bond if we shock interest rates down. This is the value of the bond if we shock interest rates up. So we start with the bond value today, whatever that is, BV0, and we say, look, if interest rates go down by 50 basis points, the value is going to go up to here, BV sub minus. And if we shock interest rates up by 50 basis points, the value is going to go down to BV sub plus. Interest rates go up, the value of the bond's going down. So these, in the numerator here, we see the shocked values of the bond, okay, and it's going to be the difference between BV sub minus less BV sub plus over 2 times the bond value today times whatever shock we're using. Okay, this is convexity. Remember, convexity is what we're looking at, the correction to the duration measure. So duration is looking at duration is a linear measure, and the price yield function is curvilinear. So that's going to cause some problems for us. So real quickly, so looking at, no, not time, looking at, if we're looking at price against yield down here, okay, well, the actual price yield function is going to look like this. It's nonlinear, but if we go in and we say, well, what is the duration measure? Well, the duration measure is going to be linear, so it's going to be something like this. So notice that as we use duration, we move along the blue line. Well, we end up misestimating the value or underestimating the value of the bond down here, and we underestimate the value of the bond up here. Convexity is the correction for that. So duration will work well if we're talking about little changes in interest rates, down here. But if we're talking about big changes in interest rates, this is the current rate level, then we're going to need to use this convexity correction to make it right. So I would put both of these on my formula sheet in order to make sure that I could deal with them, although I think it's probably more likely that they would just tell you that this is equal to 7 and that this is equal to 11 or 17 or whatever it happened to be, and then ask you to use them. So you ought to know how to use those in the exam. We talked about this when we talked about using the effective duration number when we talked about using key rate duration. So this convexity, remember, that's just a correction that has to be used in conjunction with duration. Now, notice that we labeled this ED in EC, effective duration and effective convexity. There's a labeling difference here. Modified means that we're not considering any change that interest rates will have on the bond's cash flows. Effective means that we have considered that. The formula is the same for both of these. So if they say effective duration, that means it's a callable or puttable bond. If they say modified duration, that means that the bond has no embedded options. For us, it's transparent. It's just a labeling issue. All right? Okay, in that case, how do we calculate this? Well, we got this long process to go through. Obviously, you can't do it on the exam, but you're going to calculate the OAS the way we just did using the binomial model. Then we're going to shock interest rates up. We're going to build a new interest rate tree. We're going to add the OAS to each of those rates. Then we're going to compute BV sub plus. That is when we shock interest rates up. Okay, and then we're going to go back and do the whole thing again for BV sub minus. So we're going to go through the whole process 3 times. Once to find the OAS, then once when we shock interest rates up, once when we shock interest rates down, and that is going to become the BV sub 0, BV sub plus, and BV sub minus. Obviously, we don't have time to do a lot of that on the exam. All right. Now, last topic here. and that is convertible bonds. So in convertible bonds, we're looking at bonds that can be converted into shares of stock. The thing to remember here is that this is, the call option is on the stock, and it's held by the bondholders. This is not an interest rate sensitive option, so we cannot use the binomial interest rate model. What we're really going to do is just come up with some valuation heuristics here, all right? So looking at this, we'll say, well, all right, here's the terminology for this bond. Let's come up with a little example here as we go through. And I've made one up, and I'll do some typing here so an example we can follow. So let's call the conversion ratio, okay, I'm going to call it the CV ratio, is going to be equal to 10. All right. So what that means is if for every share of stock that you have, you can convert that, for every bond you have, you can convert that into 10 shares of stock. Okay. So now we'll say that, let's see, the bond value today, so I'll make a little bigger type, the bond value is equal to, let's call it 950. Okay. So that is the value of the convertible bond today. So that's what you would pay for the bond today. The value of the straight bond, okay, if I can get that to work again. Well, okay, and I'm going to just call it ST bond. Okay, we'll call that as being equal to 900. So if the bond didn't have any call features in it, it would be worth $900 just based on its interest rate. Okay, the stock value is going to be equal to $85 a share. Okay, just as an example here. So if we have this bond, well then we can, we have this bond that's worth 10, that we can convert into 10 shares of stock. Each of those shares of stock is worth $85. Well, that's going to give us some stuff to work with. Let's say that the bond has a coupon here. And if I can get back to my right tool, the coupon, we're going to call it 5%, and I'm just going to put that in here to remind us, 5% coupon. So what does that tell us? Well, if we go and start looking at the conversion metrics here, the conversion ratio is 10. The market conversion price, that's the effective price when you're converting. So that is the market price of the bond. Okay, the market price of the bond divided by the conversion ratio. So in our case, that's going to be the price of the bond, which is $950 divided by 10. So that is for us is going to be equal to $95, right? So if we bought the bond and immediately exercised, it would be like buying the stock for $95. The conversion value is going to be the market price of the stock after conversion times the conversion ratio. So that's going to be 85 times, whoops, sorry about that. So that's going to be, if I can get that on there, 85 times 10, since we get 10 shares of stock, and that's going to equal $850. So if you bought the bond today for $950 and immediately converted, you'd have $850 worth of stock. Not a very good deal, right? So what about the straight value of the bond? Well, that was given to us at $900. The minimum value of the convertible bond is the greater of the conversion value. So that's the $850 or the straight value. So the stock value, if the stock price is low, this will trade like it's a bond. It'll look like a straight bond. If the stock price goes way up, then it will trade like stock at something close to its conversion value. Getting to the important part here, the market conversion premium is the market conversion price, okay, which is going to be $95. So that's going to be $95. Minus the $85 that of the value of the stock, so that's going to equal $10, right? So this would be like buying the stock at a $10 premium. Okay, the market conversion premium ratio is just this market conversion premium, $10 divided by $85. I think that's close to 12%. If you see this on the exam, my expectation is that the problem would surround these two variables, the favorable income difference and the market payback period. So looking at the favorable income difference, the annual coupon, so this is the coupon if we own the bond. These are the dividends if we own the stock. So in this case, I didn't type it. We're going to say the dividends are equal to 0. Well, the coupon is going to be equal to what? Well, the coupon is 5% is going to be $50 minus 0, since the stock is a 0 dividend payer. So that's just 50 minus 0 or 50. And then we divide that by 10. Okay, that's going to equal $5 per share. So holding the bond is like holding the stock and getting a $5 dividend. So that's the favorable income difference. Then the question is, given that $10 premium, how long does it take us to get paid back? Well, we said the premium was $10 and the favorable income difference of holding the bond is 5. So that would equal, and I'm not sure I can write this in here this close to the edge, would equal 2, meaning that the premium payback period is 2 years. So if you buy the bond, you're buying it, and of course the option's always out of the money. Okay, but because of the favorable income difference, if you hold the bond for 2 years, you will have gotten back enough of a favorable income difference to offset the premium associated with buying the convertible bond. You can also calculate the premium over straight value. That's just going to be 950 over 900, and that'll tell you how much of a premium you're paying for the bond. So to wrap things up, so if we're looking at a non-callable, non-puttable convertible bond, well, the bond value is going to be like the straight value of the bond plus a call option on the stock. This is what we would call a contingent claims valuation methodology. So here we're looking at just a pure convertible bond. What about a callable convertible? Then we have 2 options. So we have the straight value plus we have the call on the stock that we own minus the call on the bond that we gave to the stockholders. So the point here is that a convertible bond is simply a straight bond plus the value of the embedded options. All right. Okay, so looking at some volatility stuff here in the sense of what's going to happen, the effect of interest rate volatility on changes in the callable convertible bond. So what's going to happen to the value of the callable convertible bond if the volatility of the stock increases? Well, remember, we own a call option on the stock. If the volatility of the stock goes up, that's going to increase the value of the option we own. That's going to increase the value of the callable convertible bond. If the value of if the volatility on rates increases, well, that's going to increase the value of the call option on the bond, but we're short the option on the bond, so that's going to be driving down the value of the callable convertible bond. And if interest rates increase, well, that's going to drive down the bond value and hence also drive down the value of our callable convertible bond. So the point here is the value of the convertible bond limits downside risk. If we're choosing between the two, we buy the convertible bond or we can buy the stock. If you buy the bond and the stock goes in the toilet, okay, well then you still have the bond value. So if you buy a convertible bond and the stock price is constant or goes down, then we're going to see that with the stock price going down, the convertible bond will outperform the stock. If the stock price goes up, then we're going to say, wow, I wish I just bought the stock instead of buying the bond and paying that premium. Then the stock price will outperform the bond. And as I said, under a market where we have a flat stock prices, the convertible bond is going to outperform, assuming no changes in interest rates, because of the income that we receive from holding the bond. And that wraps up this relatively detailed reading. What do we need to know here? Absolutely, you've got to be on top of this binomial model in terms of where it comes from and interpreting the tree. Remember, you don't have to derive the tree. Okay, the idea of backwards induction is important. You need to be able to use the model to value a callable bond. I would add you should also be able to value a puttable bond. Find the value of the embedded call. You must know the spread measures. So I think the spread measures is one of the most important topics in all of the fixed income measures, or in all the fixed income material. We'll see that again when we talk about asset-backed securities. And then a little bit on convertible bonds. Mostly this is terminology and evaluation and valuation metrics and those types of things. Maybe some stuff on the risk-return profile. Okay, that's a lot of material. It may take a little getting used to. What I would advise you to do is to get down the basics of the binomial model first, then move on to the OAS, and then worry about the other aspects of this material. So it takes a little time, but you can do it, and you're very likely to be rewarded on the exam because this is stuff that is easy to write test questions on.